Right, we're learning about indefinite integrals of exponential functions, and we're going to start with base e. So this video assumes that you know and can remember your derivatives for exponentials. So with that in mind, let's go through or derive a few rules here based on our previous knowledge. So since the derivative of e to the x is e to the x, from our previous knowledge, easiest result in the world to remember, isn't it? The integral of e to the x dx is e to the x plus c. Shouldn't be any great surprises with that one. So there's one for you. So the integral of e to the x is e to the x plus c. So we can continue on. So if we have something a little bit more complex there, so if we have the derivative of e to the ax plus b, so the exponent is a linear function. The derivative of that was a e to the ax plus b from our previous work. So thus that means that the integral of e to the ax plus b dx would have to be 1 over a e to the ax plus b plus the arbitrary constant of integration. So we have two results so far. Now for the third one involving base e. And we also learnt the derivative of, basically this is an application of the chain rule, function of a function. So e to some function f of x, that would, due to the chain rule, that would be the derivative times e to the f of x, where f of x is some function of x. Now, if we take the integral of that result that we see on our left, so the integral of the derivative of some function times e to that function, let me make that derivative there, it's a little dash for derivative. Let me tidy that up. Okay, so therefore that will be reversing this here, and we would get e to the f of x plus the constant of integration. Okay, so if in other words, if you have e to some function and you can see its derivative on the front, if we integrate that, it's e to the f of x plus c. So there's your third result there. Make sure you take note of those. They are important. So there's the three we're going to be using that involve base e. Now for some examples, two examples there, and let's look at the one on the left first, example 1. So we have pretty much the closest fit there. You could use rule 2 or 3. They're basically the same thing anyway, but whether you consider it as rule 2 or rule 3, probably rule 2 is a bit more direct. They are essentially the same thing. If you like, it's your choice. You can put the constant out the front, and we have an ax plus b there. That's 0b, alright? Doesn't matter. Just so you can see it fitting there. And we have 1/4 times 5, which is 5/4 e to the 4x plus c. Example 2 now, we have basically the example of the third rule, so I'll leave that showing there, because you can see where f of x, you may want to write this down, f of x is x cubed minus 1. So the derivative is 3x squared. Okay, now here's a little trick. Write down, it doesn't quite fit the form. Alright, we want x squared, and for it to fit the form it needs to be 3x squared. So write down what you want it to be, and I want it to be 3x squared, like so. But of course it wasn't 3x squared, it's 1x squared. So we have to times by a third as well, and you can put that out the front. Okay, so there we go. And now that fits the form, and so the answer is a third times that. Alright, so it's a third times e to the x cubed take 1 plus c. Alright, e to the x cubed take 1 plus c with a 1/3 on the front. You don't have to multiply the constant by a third. A constant is a constant. What if the base is not e? So if we've got something in a to the x where a doesn't equal e, well, we knew from our previous work that the derivative of a to the x is a to the x log a, or if we switch it around the other way here, as you can see, I just switched switched it around. The equal signs been switched around, the order's switched around. So if we take the integral of both sides with respect to x, we'd have the integral of a to the x log a. Remember, log a is a constant. On the right hand side, we would be undoing the derivative, so we would just have a to the x, the integral of so integrating both sides. Integrate both sides. That's what we're doing there. Alright. And that would just be a to the x. Of course, there's got to be a plus c there too. Actually, I just changed the c to a k because we're going to use c later on. K is just the constant of integration, okay? Now, if we multiply both sides by 1 over log a, and 1 over log a is just the constant. So once we multiply it by both sides, we get that. So the constant does get multiplied by that, which creates a different constant. See, we'll get a new constant. That's what I'm calling c. So that k divided by log a, once we do the dividing, is a constant as well. Alright? Now on the left, basically, because that's a constant, there, we can pull that out the front. And once it gets multiplied by that, that'll be log a over log a, which is 1. So we basically just have the integral of a to the x dx. Sorry, I should have had a dx written there on the left side of the equal sign. And that's what we're trying to find, right? If you go back to the start, that's what we were trying to find. So the integral of a to the x is what we have here on the right. And so we've got a to the x over log a plus c. Alright? So that's our final results there for the video. Result number 4. Okay, so if we have to use that in an example, we've got a base, other than e, we've got a base of 2 there, and let's take the integral of that. Now, using your index laws, we can go, that's integral of 2 to the 3 to the x dx, because that's your power of a power index. So let a now be 2 cubed. It's just a number. You could write 8 if you want, but I'm going to leave it as 2 cubed. And so just following the process there, we have a to the x, so that's that's 2 cubed to the x over log of a, so that's over log of 2 cubed, and that would mean that's 2 to the back to the 3x again, the way it was. That's why I didn't change it to 8. If you change it to 8, it'd still be okay, and that's over log 2 cubed, or we could write 3 log 2, and that's the most elegant way of writing it. Okay, so 2 to the 3x over 3 log 2 is our answer.